Okay, so this is the 2023 Higher Level Applied Maths paper question 4. A ball of mass m kilograms is projected with initial velocity 15 meters per second vertically downwards into a tank of water. The ball travels through the water against an upward buoyancy force that is 4 times the magnitude of the weight of the ball and a drag force of mv squared newtons. Draw a diagram to show the forces acting on the ball while it is moving downwards through the water. Okay, so we have our ball here, mass m. You're going to have the weight acting downwards, which is mg. Two forces acting upwards. One is an upward buoyancy force that is 4 times the magnitude of the weight of the ball, so that's going to be 4 mg here, and also let's see, what a drag force of mv squared, so this is mv squared here, newtons, and it's going downwards, so there'll be an acceleration downwards here. Really, that's it. That's all we have to do there, I think. Let's have a look at part 2. Show that while the ball is moving downwards, the rate of change of its velocity v with respect to its distance s below the surface of the water can be expressed by the differential equation v dv ds is equal to minus 29.4 minus v squared. Okay, so let's have a look at all the forces acting on the ball. We have mg acting downwards, these two acting upwards. It's moving downwards, so mg is going to be bigger, so we're going to put mg first, and then we're going to subtract 4 times mg, and we're also going to subtract the mv squared. That's equal to, they're the forces acting on the ball, and that's equal to mass times acceleration. So mass times acceleration. Now the mass times acceleration, that's going to be m times v dv ds. Remember that acceleration can be written as dv dt or v dv ds. We have v dv ds in our equation up here, so that's what I'm changing acceleration to. Okay, so let's just delete all the m's, or cancel them all, or divide across by m. So that will give me, let's see, g minus 4g minus v squared is equal to v dv ds. So we want v dv ds on its own, that's fine. So over here we just need to work out g minus 4g. So if you do that on your calculator, 9.81 minus 4 times 9.8, I should say, 9.8 minus 4 times 9.8, that will give you minus 29.4. So you get minus 29.4 here, minus v squared is equal to v dv ds, and that's it really, that's all we have to do. Let's move on to the next one. Solve this differential equation to find an expression for v in terms of s. Okay, so let's just write it down first. So we've got v dv ds is equal to minus 29.4 minus v squared. So let's just get rid of that ds on the left hand side. V dv is equal to minus 29.4 minus v squared times ds. Now divide across by this bracket here. That would be v over minus 29.4 minus v squared dv is equal to ds. So what we need to do now, we have all of these on the left hand side, s is on the right hand side, so we just need to integrate both sides. And on the left hand side, remember, we're starting at 15, the velocity is starting at 15. A ball of mass m kilograms is projected with initial velocity 15 meters per second. So we're going to start here on the left hand side with 15, and we're going to go up to some final velocity v. The distance, well, we're starting at distance 0, we're going to some distance s. So let's just integrate all of these. Now on the left hand side we have v over minus 29.4 minus v squared. So if you look at this, we really have 1 over this here. And if you integrate 1 over something, you get the log of the something. So I'm going to start with that anyway. So I'm going to say log minus 29.4 minus v squared as my initial answer. I'm doing this really by inspection, if you like. So is that correct? Well, the log of minus 29.4 minus v squared, if we were to differentiate that, we would get 1 over minus 29.4 minus v squared anyway. And then because it's not log of v, it's log of some function of v, we've got to differentiate what's inside the bracket as well. We're using the chain rule. So if you differentiate what's in here, you'll end up with an extra minus 2v. So we don't want minus 2 there. We only have a v up here, so we need to get rid of that minus 2. So we really what we need to do here is just divide by minus 2. And that will give us all of this divided by minus 2, which will give us what we're looking for. Okay, so that's really it by inspection. So let's just put our limits in. So we got 15 and v. On the right hand side then, we've just got 1 ds, if you like. So if you integrate 1, you're just going to get s, and 0 and s are our limits. Okay, so let's just work through all of this then. Now we've got to put in v in here, and then we've got to put 15 in here. So we're going to get log minus 29.4 minus v squared all over minus 2 minus log minus 29.4 minus 15 squared all over minus 2. And then on the right hand side it's just going to be s minus 0. You put in the s, you put in the 0. Okay, so next thing I'm going to do, what I'm actually going to do is I'm going to take out this minus 2 here. So I'm just going to factorize that out, minus a half. So inside the bracket then, I'll be left with this and this. And they're going to be subtracted. So the log of something minus the log of something is just going to be the log of the first one, minus 29.4 minus v squared, divided by the second term here, which is minus 29.4 minus 15 squared. So I've done two things at the same time there. I've factorized out this minus 2, it's actually minus a half, and then I've combined these two logs here using the laws of logs. On the right hand side then I've just got s. Okay, so next thing I'm going to do is I'm going to multiply across by minus 2. So I'm going to be left with log of minus 29.4 minus v squared over minus 29.4 minus 15 squared here. On the right hand side I'll end up with minus 2s. Okay, so the next thing I'm going to do is I'm just going to move over here because I've run out of room here, but I'm going to do two things at the same time here. First thing I'm going to do is I'm going to change this fraction because there are a lot of minuses in there. I'm going to change them all to plus, and the way I'm going to do that is I'm going to multiply the top by minus 1 and the bottom by minus 1. That won't change the fraction, it'll just change the way it looks. I'm effectively just multiplying the fraction by 1 in the form of minus 1 over minus 1. The second thing I'm going to do is I'm going to change this from log format to index format. There's an e here, this is log to the base e, so it's going to be e to the power of minus 2s is equal to all of this here. So that's what I'm going to do over here. So I've got e to the power of minus 2s is equal to 29.4 plus v squared divided by 29.4 plus 15 squared. Now the idea here is to get v on its own, so I need to isolate this v. So the first thing I'm going to do is multiply across by the denominator. So I've got, let's see, 29.4 plus 15 squared multiplied by e to the power minus 2s is equal to 29.4 plus v squared. Okay, so the next thing I'm going to do then, I'm just going to multiply this out. 29.4 plus 15 squared, that's 254.4 e to the power minus 2s. I'm going to bring this over, so it's minus 29.4, and that'll leave me with a v squared, so I'm just going to square root both sides as well. So that's what I'll end up with. The square root of 254.4 e to the power minus 2s minus 29.4 is equal to v. And that's really it. That's our equation for v. I think that's really all we had to do here. Let me just double check that. solve this differential to find an expression for v in terms of s. So we've done that. Okay, let's look at the next part of the question. The ball is at maximum depth d when v is equal to 0. Calculate d. Okay, so we have our expression for v here. So we have v is equal to the square root of 254.4 e to the power minus 2s minus 29.4. So when it's at its maximum depth v is 0. So we're going to put 0 there, square both sides if you like. So we got 254.4 e to the power minus 2s minus 29.4. Okay, so that will give me, let's see, we have 29.4 divided by 254.4 is equal to e to the power minus 2s. So I've just brought this over and then I've divided by this as well at the same time. So what you can do now is just change this into log form or get the log of both sides, whichever way you want to look at it. But you end up with, on this side here, well, we'll say on this side here first, log 29.4 over 254.4 is equal to minus 2s. I've just got a log of this side and the log of this side. So next thing I'm going to do, I want s on its own, I think, isn't it? Calculate d, the distance, so we want s. S is our distance, if you like. So s then is just going to be equal to all of this divided by minus 2. So you can do that on your calculator. Take all of this, divide by minus 2, and you get 1.078956579 and so on. It goes on for a while, and that's in meters. Again, it doesn't say to give your answer correct to any number of decimal places, so we'll just leave it like that. Okay, so next question then. After reaching its maximum depth, the ball changes direction and begins to move upwards through the water. Draw a diagram to show the forces acting on the ball while it is moving upwards through the water. So this is going to be the same as what we did in part 1, but in the opposite direction. So again, we have the ball here. It has mass m. There are two forces now going to be acting downwards and one force acting upwards. The force acting upwards is the buoyancy, which is 4 times the weight. So it's 4 times mg. We still have our mg acting downwards, and we have this mv squared as well. That was, if you remember from the very beginning here, that was this here. It's called a drag force. Okay, so that's really it. Again, we have our acceleration, of course. Our acceleration this time is going to be acting upwards. Write down a differential equation this time for the rate of change of the velocity v of the ball while it moves upwards through the water. Now I presume this is the rate of change with respect to distance, the same as what we have up here. It says show, yeah, we have dv ds here, so it says up here, show that while the ball is moving downwards, the rate of change of its velocity with respect to its distance. So that's what we did here. I presume this is the same thing again here. So let's do that then. So again, we have force is equal to mass times acceleration. So this time, if we look at all the forces, it's moving upwards this time. So we've got the 4mg first. We've got to subtract the mg and the mv squared. That's equal to, again, our mass times acceleration, and which is just going to be equal to mass times v dv ds. So again, if you do all of this and cancel all the m's, divide across by m, here you'll have 4g minus 1g, which is 3g, and then we've got our v squared here, and over here we've got v dv ds. Now it says here, write down a differential equation. Really, that's it, but you could, I suppose, work this out. That becomes 29.4. 3 times 9.8 is 29.4 minus v squared is equal to v dv ds, and you could go one step further if you like. Dv ds is equal to 29.4 minus v squared over v, if you wanted to go that far. Now I'm thinking here as well that, acceleration is also dv dt, so what we could do here is just substitute dv dt in here instead of v dv ds. So that would just give us 3g minus v squared is equal to dv dt. So we would end up with 29.4 minus v squared is equal to dv dt. So I'm not sure which one they require, but we can have a look at the marking scheme anyway when it comes out. Okay, so that's it for this question.